Hi friends, welcome back to Edupedia World. Last three lectures we have focused on the theory of current electricity about resistance, resistivity, Ohm's law, ohmic and non-ohmic resistors, those kind of things. Today we'll go to the practical application of those things and see numericals based on the concepts we have learned in previous three classes. So let's start with today's lecture. The first question that we are going to discuss is based on the Ohm's law. Let's see. We have a bulb of 200 volt and it draws a current of 0.5 ampere. So let's write the given quantities. Voltage is 200 volt and the current supplied to it is 0.5 ampere. Now the question asks us that we need to find the resistance of the bulb. Okay, so quantities we have is V and I. We need to find out what is R. Now if you go back to your lecture notes and recall what was Ohm's law, we know that V is I times R. This is our Ohm's law. Here in this particular question we have been provided with the voltage 200 volt. We have been said how much current is it drawing, that is 0.5 ampere. All we need to find is the resistance. So everything is basically provided in the question. We'll use this relation. R we can write as voltage upon current. Voltage is 200 volt. Current is 0.5 ampere. So everything is in SI unit, voltage ampere. So this will give me 400. We know that the units of resistance is ohm. So our answer to the question what is the resistance of the bulb is 400 ohm. So this was a pretty easy question, and most of the Ohm's law question will be similarly easy. It won't be very difficult, but this is a fundamental idea that you need to ingrain. Therefore I wanted to discuss one single question based on it. Let's see another example. This is our second question, which says that a wire is provided which has a length L and area of cross section A. This wire has a resistance R. We stretch the wire such that the final length becomes 4L. We are asked to find the final resistance. So let us write down what are the given parameters. Length, the initial condition I am writing here, I initial condition. Length is L, area is A, and as a result my resistance is R. Okay, now we know that R is rho times L upon A, rho L by A. So this is my fundamental definition of R, and rho is the material property. So even after stretching the material, rho will remain constant. Let me find out what is rho. Rho will turn out to be R multiplied by A time divided by L. This is my rho for the material, which will remain constant. Let's say this is equation number 1. Now the second condition says that the length has been increased to what length? 4 times the L. So my final length becomes 4L. Now the question does not say anything about the final area. But as you can imagine that if you take a wire and you stretch it, then the radius of the wire or the area of cross section of the wire will reduce, right? Because the wire is extending. Where is the material coming from? It is becoming thin. Therefore the area will not remain A. It will not remain A. It will change. By how much will it change? To find out that, we need to think how can we think about that. The total amount of material in the wire is not going to change, right? Initially the amount of material will be equal to the final amount of material. Now what is amount of material? Amount of material is basically the volume of the body, isn't it? So suppose we had this as my initial condition. This would be L and this would be this whole cross-sectional area. Use another color. This whole cross-sectional area would be A. Fine. Now what has happened is that the length has increased to 4 times L. 4 times L. Therefore this area must have reduced. This area is no longer A, but we can find out that area by doing volume equation, by equating the volume. So what was the initial volume? Initial volume was area times the length, AL. What is the final volume? Let the final area be A dash and the final length is 4L. So A dash times 4L. This will give me A dash is equal to A times L upon 4L, which is A upon 4. So my area has reduced by a factor of 4 when my length increases by a factor of 4. This is my volume conservation. Volume conservation. With this idea, let's proceed. We just found out here that rho is R times A upon L, and we need to find out the resistance, the final resistance, right? So we have our length, final length, we have our final area, and we have the resistivity of the material. So we can use the standard relation R is equal to R final. Let me put it as R dashed is equal to rho times length upon area. Replacing the values, rho is R A upon L, final length is 4 times L, and final area is A by 4, so that is 4 upon A, isn't it? Now if we cancel out L with L and A with A, what we have is 4 cross 4, 4 times 4 is 16, and R. So my final resistance turns out to be 16 times the initial resistance. Therefore, by stretching the wire from length L to 4L, we have actually increased the resistance 16 times. Okay, this gives you insights about the resistivity. Here we understood that since the material is the same material, we can use the constancy of resistivity. We use the relation R is equal to rho L by A. We use the volume conservation, and combining all these small ideas, we solve this particular question. Fine. We'll do a final question and then we'll close today's lecture. The last question that we are going to discuss in today's lecture says that we need to find the resistance of a 100-meter long aluminium wire. The resistivity for the aluminium wire is given to be 2.63 into 10 power minus 8 ohm meter, and we are said that the area of cross section of this 100 meter long wire is 10 to power minus 4 square meter, so it is quite thin. Let's write down the data available. We are provided with the length L is 100 meter. We are said that the area of cross section A is 10 to the power minus 4 meter square, and the given resistivity rho for aluminium is 2.63 10 to power minus 8 ohm meter. Fine. Now we need to find the resistance. Resistance, as we have discussed, is rho of the material multiplied by length of the wire divided by area of cross section. So it's basically plugging the values into this relation. Rho is 2.63 10 power minus 8. Area is rather the length is 100 meter, 10 power 2 we can write it, and the area of cross section is 10 to the power minus 4. On readjusting it, minus 4 and 2 becomes 6, and 6 and minus 8 minus 2, so this turns out to be 2.63 times 10 to the power minus 2 ohm. Okay, so we get the resistance of our thin 100 meter long aluminium wire to be 2.63 into 10 power minus 2 ohm. Now imagine, in place of this aluminium wire, imagine if we had, let's say, something made out of glass. For example, if we had glass wire, I don't know, but let's imagine the resistivity. Let's assume that the glass would have a resistivity order of 10 to power 10 ohm meter. Then what would have been the resistance? The resistance would be, for the same length and same area of cross section, the resistance would have been 2.63 10 to power minus 8, rather, sorry, this I have written for aluminium. We need 10 to power 10, that is for the glass wire, times length is 10 to the power 2 upon area 10 power minus 4, and this whole thing turns out to be 10 to the power 16 ohm. This is enormously large, 10 to the power 16, that is 1 with 16 zeros following it, whereas this was, how much was this? If we remove this, it would have been 0.0263 ohm. Just see the order of difference. So rho, the material property, has a very large impact on what the ultimate resistance of the material or the wire is going to be. Fine. This brings an end to our discussion today, and the topic of resistance, Ohm's law, resistivity. Next class we'll discuss what is known as electromotive force, terminal voltage, resistance of a cell, and the combination of resistance. So till the next class, have a great day. Goodbye.